This is an example from the textbook by Hodge and Taylor. This is problem 218 in the chapter on heat exchangers. And I'm going to solve this problem using the Microsoft Excel add-ins that have been developed and are available on the website at www.me.ua.edu. I'll try to display that here for those that may not know where to find them. www.me.ua.edu, and if you go there to the Excel in ME website, www.me.ua.edu/Excel. I think alternately, if you trust Google, if you just search for Excel in ME, I think it comes up pretty quickly to the top of the page. So these add-ins that we're using for this solution are the heat transfer add-ins, but we're using them from the thermal systems page. You can get them in either place, but we're using the heat transfer add-in and the thermal properties of water and air add-in. Okay, well, back to this problem from Hodge and Taylor. It says there is a heat exchanger that has one shell pass and two tube passes. And it has a known overall heat transfer coefficient, of 280 BTU per hour per foot squared per degree Fahrenheit. The shell side is water, and it is given specific heat of 1 BTU pound mass per degree Fahrenheit, and it flows at a rate of 18,000 BTU, 18,000 pounds mass per hour. So it enters at 500 degrees Fahrenheit, and it says on the tube side, inside the tubes, oil is flowing with a specific heat of 0.85 BTU per pound per degree Fahrenheit, flowing at a rate of 50,000 pounds per hour and entering at 80 degrees Fahrenheit. So the water exits at 201 degree Fahrenheit. So for this given situation, the first step is to find the area of heat transfer that is required. I don't have a very good sketch of this problem here. I guess we could try to show it that we've got water in and out on the shell side, and then we've got oil in and out on the tube side, and maybe we could make those a brighter color just to I guess actually the water is the hot and the oil is the cold, but we'll just show it like this, and that we've got hot water in at 500, and it is to be cooled to 80 degrees Fahrenheit by flowing oil in here. Sorry, it's going to be cooled to 201 degrees Fahrenheit by using cold oil. I guess we're heating this oil is really the task at hand, is to heat this oil by using this hot water. Well, regardless, the flow rates are given, and we can calculate the heat capacitance of each flow stream, that is the mass flow rate times the specific heat for each one. I guess I just gave that number, just typed it in. Yeah, maybe this one is calculated. Yes. So I just gave those as the given information. Mass flow rate of 18,000 pounds per hour multiplied by 1 BTU per pound per degree Fahrenheit. So this is the heat capacity for each of the flow streams. We're going to use the effectiveness NTU method to solve this. And so the given information is here. So the first order of business is to find out which of the two fluids is the minimum fluid. By minimum fluid, we mean the one that has the smallest capacitance, m dot c sub p. So of course we can look and see that the hot water has the smaller value of capital C. CH is the smaller number, and we see that here. The next task then is to calculate the heat removal that's required for this exchanger. We know that because we were told the hot water temperature in and the desired hot water temperature out. And so knowing that heat capacitance, we can calculate the heat transfer required as simply the heat capacitance m dot c sub p times that temperature change for the fluid. So from Q actual, if we can then find the effectiveness for this exchanger, then we can find the number of transfer units, and that's going to lead us to the area that's required for this heat exchanger. So to get the effectiveness, we need to now calculate the maximum possible heat transfer for this exchanger, and that will result if the minimum fluid undergoes the maximum possible temperature change, which is T hot minus T cold. T hot in minus T cold in. That's the maximum temperature difference in the exchanger. So the ratio of the actual to the maximum temperature heat transfer gives us the effectiveness, and this effectiveness is required is 0.71. So now we're going to use the add-in software called HXNTU to calculate the number of transfer units for this type of exchanger for that effectiveness. We can find out, if we have a Windows system, we can find out more about these functions through the online help that is built into these add-ins. And you can see in the small print here that there's a description that indicates this first parameter in this call is a descriptor to indicate which type of heat exchanger we have. So 1 and 2 or other types. Type 3 is a shell and tube with one shell pass, and that's what we have for this heat exchanger. It has a single shell. So we put in the value of 3, we put in the effectiveness that we calculated. We need to put in C min and C max, the way these functions are arranged or for the input. We need to put in C min and C max. So C min was the 18,000 and C max was the 42,500. When we put all that in, the calculation comes back and says the number of transfer units is 1.94. So how does that help us? Well, number of transfer units is equal to UA over C min. So we can now rearrange that equation to solve for the area that's required as being NTU times C min divided by U, and U is given. So for this exchanger, we find out 125 square feet of area is what is required. Probably a more reasonable way to represent that is by actually rounding the number off. So there we go, 124.9 feet squared. The second part of this problem is a little more interesting. It asks us to develop a plot showing the outlet temperatures of the water streams, cold and hot water streams out, cold oil out and hot water out, if the water flow rate varies from the 24,000 down to 0. And it says we should assume that the overall heat transfer coefficient remains the same, the given 280 BTU per hour per foot squared per degree Fahrenheit. The reason the specific instruction is given there, certainly as the water flow rate changes, then the heat transfer coefficient associated with the water movement over those tubes will change. And we're asked to ignore that or to assume that the effect is relatively small. So we're just going to hold this overall heat transfer coefficient constant. And we're also going to keep constant this area that we just determined. We're going to assume that this heat exchanger operates, once we've sized this exchanger, that it's going to operate with these varying flow rates. So here's what I'm going to do. I'm going to set up a variation. It says he wants us to go down to 0. I don't know if we can do that. I'm going to go 1,000, 5,000, well, maybe 6,000, and then 12,000. I don't know. That doesn't give us very many points, does it? It wants us to go to 24,000. Yeah, that's too much. Let's go half that fast. Get a few more points, and take that up to 24,000. There we go. So we're going to vary the mass flow rate of the water, and then the specific heat capacity, m dot times c to p. This is just equal to, I'm going to go ahead and do this. This is equal to m dot v times 1. Why is it times 1? Well, the specific heat of water for over a wide range of temperatures is about 1 BTU per pound per Fahrenheit. So these numbers are the same. The CV, the heat capacity, is numerically equal to the mass flow rate. What are we going to need to do? We need to make sure that the minimum fluid isn't going to change, just so we're careful in our analysis. And it looks like because the cold oil flow rate is so high, that the minimum fluid is not going to change. So because CC is 42,000 and the maximum value we have here is 24,000. So we're good on that score. So now what do we need to do? We need to basically repeat these same calculations that we did here to find, well, actually to sort of recalculate what we did here. In this case, we're going to fix the area, keep that constant, and so we know U times A, and that's not going to change. But what is going to change is C min. This is basically our C min column right here, and it's going to change each time. So let's make a new column called NTU varied, and that's going to equal to U times area, but divided by this thing I called CV. And so these are the values of the NTU that are required to for these parameters with U, A, and C min. And so now for each one of these, we want to invert this and use that NTU to calculate the corresponding effectiveness. So to do that, we're going to make use of the add-in equations again. Heat exchanger effectiveness, and this was the type 3 heat exchanger. and we now need to give the NTU and the Cmin, which is CV, and the Cmax, which didn't change, which is CH. And it doesn't hurt, we can tell it that it's 2 passes in this heat exchanger. I'm getting this ugly error here because I failed to define these names that I used in this equation, and I just need to straighten that out. What's he telling me? Let me double check. Effectiveness. I think that NTU value may be too high, so let's just see if we can get some good results here. Maybe I'm not filling the blanks correctly, so let's take a look and see. NTU, and yeah, what he doesn't like is NTUV, this varying, and CV. I see CV. Let's put a fix on that. Yeah, these functions are expecting scalar numbers to be passed to them as parameters, and you can see that when I defined NTUV, that it's actually a vector of numbers, but also CV is a vector of numbers. And I'm using a little trick here to multiply that vector times 1 before I pass it into this function. And when I do that, Excel will do that multiplication, and we'll pull out the value from the current line to do that multiplication. And that's exactly what I need to happen. So that's a little trick that comes in handy when you have a range of values or a vector of values, and you're just trying to process them line by line, just to you let Excel multiply by 1, which doesn't change the number, but it does force Excel to go ahead and pull out that one value of CV in this case and NTUV to pass to the function for us. So anyway, these then are the effectiveness values. We can now calculate Q actual for each one of these cases. And how would we do that? Well, it's the effectiveness, but now we have to multiply by the Cmin, which is our CV, and then we have to multiply that times the maximum temperature difference in the exchanger. So the effectiveness times Q max will give us the actual heat transfer. So for each case we have this, and now he didn't ask us to find the heat transfer. He wants us to make a plot of the T hot and the T cold. So how do we get those? Okay. So now we're supposed to have a plot of this, and we can make such a plot for the mass flow rate and the hot and the cold, and let's insert a chart here. Yeah, so without dressing this up too much, see if we can make it a little smaller though. Yeah, that's how the temperatures vary as the mass flow rate of the hot water increases. So this is the exiting temperature of the cold fluid, the oil in this case, and the exiting temperature of the hot fluid, the water. So that's it. That's problem 218 from Hodge and Taylor.